second because I want to close this window. Perfect. Very good. So recording started, and we can move forward with the next lecture, the next topic. We talked about history of Earth's climate last time, and I mean, it was a voyage in the past, a voyage through time. I just want to highlight before I move forward this link in my website. It's an ebook, A Travel Through Time to Explore Past and Future Mega Droughts. If you're interested, I think it's a nice reading. It's very relaxing. You know, it's an ebook. You can put it full screen, and there are several chapters, and it's maybe fun to look at history of past mega droughts. Mega droughts are something that is fascinating because, you know, sometimes it happens that for 10 years, 20 years in the past also, we think that for longer times, like 100 years, we get less rainfall in a particular region. And less means minus 20% with respect to the usual average, which means something very relevant. It's a really strong water scarcity that is originated by these long-term phenomena. We don't understand what is the reason for these durations. And the same occurs for floods. Sometimes we get cluster of floods, but anyway, this ebook deals with droughts. Okay, but let me go back to our next lecture, which is climate and energy. Okay, first, let me increase a little bit and let me get the PowerPoint, okay? Climate and energy, it is a big topic because the two things are tightly related, and this is not something that is very clear, actually. If we think at the climate issue, at the climate issues, climate problems, often we don't realize that they are tightly connected to energy production. Energy production is something new for humans. New, I mean, we started our very intensive increase of energy requirements like 200 years ago, okay? And before than that, I mean, humans were used to profit from energy, like for instance, when we are collecting water from a spring, and we are just collecting water by hand, by filling a bucket, we are actually taking advantage of energy, the energy of water that falls into the bucket, and we prefer to use this way of collecting water rather than putting a bucket into a well. It's more demanding because we need to use our arms in order to get back the bucket. And this is a use of energy which is more demanding for us because, of course, our body, our muscles can produce energy. So, I mean, from ancient times, we were used to use energy produced by our body. But when we can profit from energy that is freely available in nature, of course, we use it. So the requirement for energy is not new. A living body needs energy. Another example is when we take a bike and we go uphill, we use energy that is available in nature, when we downhill, sorry. And we are not using any energy from our body. We take the bike and run downhill. When we want to run uphill, we have to use the energy of our body. And this means that in some cases, we need to produce energy ourselves. In other cases, we can use energy that is freely available in nature, or when we put something to heat in front of the sun. So, for instance, we use during summer to heat water by putting buckets out in the sun. We use energy that is naturally available. When we want instead to warm the water by putting it on a fire, we are using fossil fuels, or not only fossil fuels. We may use other kind of fuels, but in any case, we use an energy that is not immediately available from the sun, but that we gain with other ways. So what is the moral of the story? The demand for energy is natural, is a natural need, but starting from 200 years ago, humanity started to require more and more energy after the Industrial Revolution. After the Industrial Revolution, we realized that we had the possibility of producing energy by warming water, therefore obtaining energy from steam. The steam power was a great invention who supported the Industrial Revolution. The Industrial Revolution was indeed could occur because humans discovered the steam power. It was a great discovery, a great discovery. On the other hand, it promoted an ever-increasing requirement of energy. Energy is needed in order to promote our welfare, to increase our welfare. It's needed for many needs, like for heating buildings, for driving a car, for traveling, for working at the PC, because in order to support the work of a PC, of course, we need to feed energy. So our demands for energy is increased, and this has allowed the Industrial Revolution, the great acceleration. The two things are connected. And it is like a chicken and egg, Without energy, you couldn't have any revolution, industrial revolution, any great acceleration, but great acceleration needs energy. So it's like chicken and egg. So it's hard to say whether we discovered the steam energy first or the industrial revolution started earlier. Anyway, the two things are connected. When two things are so connected, we talk about a nexus between climate, industrial revolution, anyway, human activities, energy. Nexus means that the two things are connected and there are also feedbacks, meaning that there is a feedback produced by the Industrial Revolution on energy demand, and conversely, there is a feedback between our capability to produce energy and industrial expansion. And there is a tight nexus feedback between climate and energy, because in order to mitigate climate change, in order to adapt to climate change, we need energy. We need energy, like if we want to design anything, if we want to build a dam, if we want to reduce emissions, we need energy. On the other hand, energy production is related to emissions, because as we will see, we can produce energy in many ways, but many of these ways produce emissions. So it is like chicken and egg. We need more energy. Energy is one of the drivers of emissions, and therefore climate change. In order to fight climate change, we need more energy. So we talk about the nexus, and it's important to understand these feedbacks. When we talk about decarbonization, we know that decarbonization requires energy transition. What is energy transition? We will discuss it in a minute. It means that we have to make a shift in energy production. We have to change the way we produce energy. But energy transition requires more energy, as we will see. So it's important to try to get oriented in these issues because, of course, we may say, let's fight climate change by reducing our energy requirements. But reducing our energy requirements after a certain extent means reducing our welfare. And this is something that we really don't want. So for this reason, it is important to gain a better understanding to what extent we can reduce our energy requirements, what solutions are possible in order to reduce our energy requirements without reducing our welfare, without a too high social cost. Okay. The social cost is extremely important of any solution to climate change. Social cost means the cost to the whole community that has to be shared according to some principles and some rules. And these rules sometimes cannot be easily governed, cannot be easily managed. And keep in mind that when we talk about social cost, the most affected categories by an increase in a social cost are those that are more disadvantaged. It's clear because if one has a lot of money, who cares about an additional taxation? But a person that really struggles to get to the end of the month, as we say here in Italy, which means a person that struggles with the personal budget, an additional taxation is a huge thing. It's a huge problem. And for this reason, it's important to also devise rules for taxations, which in a way ensure equity. On the other hand, these rules, as I said, cannot be always managed because they are also the result of an international agreements, and the cost, the social cost, also depends on the market. And we know that the market, it's not easy to manage the market. The market is free. So even the current debate, discussion, attention on the taxations that Donald Trump is introducing, it's very relevant. Why? Because it implies a social cost, and we have to make sure that this social cost is in a way shared according to principles of equity. And these rules cannot be easily governed, as we see for the case of the additional taxations by the US administration. So let's try to understand something more about energy. What does it mean? Keep in mind one important thing. I'm not, and once again, not an energy expert. I am much interested, like you are, and I studied, but I am not a researcher in energy. I am a researcher in climate, a researcher in the topics of climate that are related to water. I'm definitely not an expert of energy, and therefore your feedback is also important in this topic. It's even more important that we try to discuss. And if you say something that is not clear or something that it's not really matching your expectation or your personal knowledge, just let me know, okay? But I think that we will have the opportunity to learn something more. So first of all, what is energy? So if you want to really put someone if you want to embarrass someone, just ask to friends or even experts, what is your definition of energy? And indeed, it is something that, look at the quote of Vincenzo Bolzani. Vincenzo Bolzani is an Italian chemist, he's an emeritus professor at the University of Bologna. He was close to getting the Nobel Prize in chemistry, and you may, it's an interesting story. He was very close, but at the end he didn't get it. So, but he got a lot of recognition for getting so close, because at the end the final decision was something that, I mean, some people didn't agree with. Anyway, this is just out of curiosity, and if you are interested, there is a lot of information over there. So, Bolzani said the same thing that I just said, like if you want to put someone into trouble, just ask for a definition of energy, because it is something that we all know. It's clear to any of us what is energy, the meaning, the practical meaning of energy. When we say you need a lot of energy to do that, you are a very energetic person, or like, yes, this car has a lot of energy. We know what it means. But if we have to provide a definition, it is not so easy. For instance, for many people, it's not clear the difference between energy and electricity. We tend to identify energy with electricity. Electricity is a form of energy, but it's energy is much, much more than electricity. So we think like energy into our houses, electricity. And we don't realize that energy can come from the sun, Like if I go out in the sun in a sunny day, I take a lot of energy. It's not electricity, fortunately, okay? And it's electricity what I get from a thunderstorm, from a thunder. But when I get energy from the sun, it's not electricity. Still, it's very important energy. Keep in mind, all the energy in the universe, in the solar system, sorry, in the solar system comes from the sun. It is, in particular, the energy in the Earth system is provided by the sun, any form of energy. So when you, talk about fossil fuels, it's from the sun. When we talk about the heating in our houses, geothermal energy is from the sun. And so this can give you the idea that energy is something really undefined in some way. Okay, so how can we define energy? It's like how can we define probability? Everything, something that any of us knows, but if we have to provide a definition for probability, it's difficult. So let's focus on it. So first of all, the word derives from the ancient Greek, and that's fine. Just to know, and let's try to find a definition. Okay. So energy is defined in physics as the quantitative property that must be transferred to a body or a physical system to perform work on the body or to heat it. Okay, so let's read again. It's a quantitative property. Quantitative means that you can measure it, that must be transferred to a body or a physical system to perform work on the body or to eat it. Okay. So simply put, energy is the ability to do work. And we know the definition of work because you have a background in physics. Okay. Perfect. So it's the ability to do work, simply put. But let's also not forget heat. Okay. It is measured in joule, which is the energy transferred to an object by the work of moving it a distance of 1 meter against a force of 1 Newton. So 1 Newton per meter. So it's in joule. Energy is a force times a distance times a length, just to understand in terms of measuring. Okay. Good. So, of course, it is essential because in order to survive, to live, we need to produce work. In order to eat, to digest, to move, in order to produce things, in order to build houses, we need to produce work. We need to produce that quantity that is generated by a force times a length. Okay. Still, it's not very clear what is it, okay? The definition, yes, okay, but still it's not very clear. It is essential for life, then, like water, like food. And as I said, the sun, directly or indirectly, is the source of all the energy available on Earth. Can come directly in form of radiation or photosynthesis, or indirectly, for instance, in terms of fossil fuels. Well, wow, you may say, fossil fuels from the sun? Yes, because fossil fuels are originated by organic matter that lived in the past and could live because of the energy from the sun. And then this organic matter has been decomposed in the deep earth and transformed into gas, natural gas, oil, whatever, or whatever, okay? And even when you use a piece of wood to heat your house, you are using organic matter that has been grown up by using the energy from the sun. And this is indirect solar energy. Direct solar energy is what we use in order to heat our body when we relax in the sun outside. Okay. So, do we really need so much energy? Yes, because here there are some examples. First of all, we don't realize how much energy or other essential elements like water we use every day in our routinary life. We don't realize it. We don't realize that probably every day we use 100 liters of water. When we design a water supply system, our usual reference that we use in order to design the capacity is at least, at the very least, 150 liters per day per people. And really, we don't realize that in a day, it's very likely that we use 100 liters. You may say impossible. Okay, take into account that a shower is about 20 liters, and any flush of the toilet is 5 liters, any small flush. And there is the water that you use to wash clothes is not the water that you drink. The water that we drink is really a minimum amount. So in terms of energy, you see some examples here. The production of 1 kilogram of meat on average requires 7 liters of oil. Why? Of course, because you need energy. And you can measure this energy in terms of volume of oil. Okay. Desalination, we all know that requires a lot of energy. So 1 cubic meter, 1,000 liters of desalinate water costs 3 liters of oil. Okay, if you compare meat production with desalination, you may say, how it's possible that meat production is so demanding? But I think you heard that indeed meat production is one main reason of human CO2 emissions. And now you understand why, because we need a lot of energy. And you may say, what is the link between energy and emission? Of course, you will see that we still produce energy. At most, the major part of the energy we produce is by using fossil fuels. So this is why energy is related to climate change and CO2 emissions. Producing a ton of aluminum requires about 5 tons of oil. Producing a car, 3 tons of oil, which means about 25% of the energy consumed in a car in its lifetime. This means that you buy a car, you use it, you need oil. Okay. The oil that we use to make the car is about 1/4 of the oil that you will use to run it for the entire life of the car. This is something that is a bit, how to say, difficult to believe, okay, but it's true. Energy production accounts for about 75% of global greenhouse gas emissions. This is one important order of magnitude that you have to have clear. So energy production today is related to the use of fossil fuels. We produce energy by burning fossil fuels. 75, 3/4 of the energy we produce. And then we understand the impact on public health and climate change. Of course, we know that we are trying to move forward in this process of using renewables, but we are at this stage now, 75% fossil fuels. So you now understand why, when we talk about electric cars, there is some reservation, because if we use electricity to run a car, undoubtedly we are still using fossil fuels, because 75% of the electricity that you use to run the car was taken by burning fossil fuels, with one additional problem, that the conversion between burning fossil fuels, producing electricity, and using the electricity to run the car implies much more energy losses than the direct use of fossil fuels to run the car. Because from fossil fuels to running the car, you have just one conversion. You have to convert a form of energy, fossil fuels, into kinetic energy, the car. If you add an additional step, which is the electricity production, and then there is electricity transportation, of course, you add energy losses, okay? So it's not so simple. The issue is not so simple. Okay, just let me just see. Okay, energy transition. Okay, very good. So recent history, has shown that energy is also essential for international cooperation. And the recent history has shown, on the one hand, that international cooperation is essential to use energy in an efficient way. There are a lot of energy exchanges between countries. And we know that because this is actively debated today more than ever, how to regulate these international exchanges of energy. So on the one hand, international cooperation is necessary. On the other hand, very recently, in the past 3 years, we realized that international cooperation is under threat. Not only for geopolitical tensions, not only for the wars, not only for, it is under threat also because the idea of a global free market, which was our illusion for 30 years, we realized after the pandemics that it doesn't work, simply doesn't work. Because it turns out today, with every day, with additional news, that this free market, free means without any taxation for the transfer of goods, without any, without any fee on the transfer without any fees at the moment when a good goes through a boundary, okay? The fees that now Trump is putting, I'm sorry, I don't remember the English word. Anyways, taxation. I'm sorry. And the illusion was that we could live in a world where the market was completely free. And this, of course, favors international cooperation, international competition, which is good. On the other hand, we learned very recently that it doesn't work. Maybe in the future, we realize a different way of setting it. But the way we deemed it was possible, by just leaving the market free and leaving international competition free, we realize it doesn't work. We need some regulation in a way, and today looks like this is really under the need of a complete rethinking. Okay. So the idea of energy transition that we have, transition from a system that is essentially based on burning fossil fuels for energy production to a system that is completely decarbonized, the idea is probably going to take much longer to get converted into practice than we predicted. It's the idea in principle is very good, and besides being very good, it's also necessary. The idea of decarbonization, it's necessary, not only for reasons of climate change and public health, but also for reasons that the fossil fuels are going to be depleted. they are going to be exhausted sooner or later. It's hard to make a prediction, but it's clear that it's a source of energy that is not renewable. So the idea of turning into the use of a renewable form of energy is indeed a necessity. But of course, we have to find the correct solution. And this is why we are here today to discuss this. So what is the solution? The solution is solar energy. The solution is nuclear energy, just to give you an example. I was strongly against, in my youth, I was strongly against the use of nuclear energy, because nuclear energy, first of all, you have to take into consideration that is associated to the Second World War and disasters of the atomic weapons that were used in the Second World War. So, I mean, that is a kind of association that generates a kind of resistance. And then nuclear energy, after the disaster of Chernobyl, of course, it's even less accepted. So I was strongly against and in favor of the so-called green energy. On the other hand, now I realize, for the reasons that we will discuss, that probably a clean nuclear energy may be a good option. But what is energy transition? Energy transition, the definition is there, is a transformation of an energy system, which implies a structural change in both energy supply and consumptions. It implies a broad shift in technologies. It implies large investments, and it implies a change of habit of people. So people need to be convinced of, because it requires also efforts, energy transition. Investments means efforts, and it implies social costs. And therefore, people have to be convinced. Today, we use this term to indicate the transition to sustainable energy. Sustainable means renewable energy that can be renewed. And with renewed, we mean a form of energy that can be renovated during a certain span of time. And the span of time is associated to the length of a lifetime in order the energy to be considered renewable. Let me be clearer. If you renew hydropower energy, can be renewed through the water cycle. And the time required for renewing it is like a season, 1 year. It's much shorter than the average lifetime of people that now is around 8 years in the Western world. Okay? Fossil fuels is renewable for sure. It takes like millions of years, but fossil fuels can be renewed. We are also studying ways for accelerating this regeneration of fossil fuels. But still, the time required is more than 8 years. So we classify fossil fuels as non-renewable. What about, for instance, wood, okay, forests? To grow up a forest, it takes it depends on, of course, on the species, but 50 years. So we are getting close to our lifetime, average lifetime. So we still say that wood energy is renewable, but it's borderline, okay, in terms of the threshold that we had fixed. So it's important to have in mind what can be considered renewable. Another example of energy transition is precisely the Industrial Revolution, with the invention of the steam power, which involved a larger use of coal and later oil and natural gas for energy production. Before the Industrial Revolution, much of the industrial work was obtained, energy for much of the industrial work was obtained through mills mills, they use hydropower. They used hydropower. There are still some mills working, and they are using hydropower. This is renewable. But of course, it's a form of energy that you understand with respect to fossil fuels that can be moved, transported, and brought everywhere. The energy produced through mills, it's only possible where you have a suitable place. Still, we had a lot of mills in the past. Any river with a reasonable amount of water had its own mill, many mills along the river. Now they are not used anymore because it is, it is very local, okay, and it is not reliable. With reliability, I mean the possibility of regulating the energy flux by humans. Fossil fuels have this great advantage. I need energy. I put the fuel in the car and I go. If I had to run the car with wind energy, you understand the problem. There is no wind, what can I do? Or the car with the solar energy, trains, what can I do? And so reliability of an energy source means our possibility to regulate it, to modulate it. Keep in mind one important thing. Energy cannot be stored or it's not correct what I said. Electricity cannot be stored. Energy can be stored, but storing energy, it's indeed much complicated. We will see why. Much complicated. It's much, much better to produce it on the fly. When you need it, you produce it. Storing it, it's much complicated. It requires really a huge infrastructure. It's not something that you can easily store. Or you can store it into the nuclear bars, but still with complication. No? Okay. Let me just show you a figure. Given that we talked about energy transition, let me show you this figure, which I think it's interesting. And you see in the caption, click here for higher resolution. So let's click over the caption and we get a PDF. So what is this? Now I am increasing. First of all, let me give you an overall view, and then we focus with the zoom on single items. What is this? This is a prediction of the energy transition timeline in global level. A transition from where? From the use of fossil fuels to the use of renewables, okay? Non-fossil share, but actually with the green color, you see renewable. These are renewables. This transition is much complicated, as you will see, and this is a prediction of a timeline. This prediction was issued by an international body called DNV, I think, yeah, DNV, and they made this prediction, which is overly optimistic. It was elaborated in 2018. It's overly optimistic. It was already optimistic in 2018, but after the geopolitical tensions that occurred after the pandemics, it clearly is too optimistic. And what is the train of thought along this figure is to show with a graphical representation what are key dates where we can consider milestones which will mark transitions, individual transitions from each energy source to another kind of energy source. So let's focus on some examples. Okay, so first of all, we start from 2016, where 19% of the energy mix is non-fossil. I said in the other slide that we are now at 75% of fossil fuels for energy production. According to this figure, which is overly optimistic, it looks like in 2016 we were at 19% non-fossil, which means 81% of fossils. It's coherent with what I said, because after 2016, after 10 years, almost 10 years, it's in line from 80% to 75%. Actually, I think it's a bit optimistic anyway. Anyway, let's start from this 19%. And this figure also shows that they assume that the use of coal peaked in 2014. 2014 means that the fact that the use of coal peaked means that our use of coal for energy production increased a lot. And then with the use of fossil fuels, with the increasing use of renewables, they assume that in 2014 we started to decrease at the global level with the use of coal. Okay, and it is predicted to reach zero around 2020. Actually, it didn't reach zero in 2020. It's not fully clear in this figure if the prediction of zero is at the intersection with the green bar or at the base of the graph, which would mean something like 2026. Anyway, it is too optimistic, because unfortunately, after the war in Ukraine, we had to recover some energy production sources from using coal. Coal is indeed really bad, because it's not very efficient, produces a lot of emissions. And then you see in 2023, they assume that the use of oil should have peaked. This didn't occur. Okay? But indeed, there are several predictions assuming that probably we will peak with the use of oil. And another prediction in 2026, it is supposed that transport energy demands peaks, and this is not really, it is a bit too optimistic. So you see that the transition timeline, the transition implies that we rely on very strong assumptions. So indeed, the fact that transport demand peaks, what does this mean? It means that people start using massively collective means of transport. Of course, the energy consumed by a train is the same, no matter how many people are there. So if there is only the driver or a full train of people, the energy demand is the same. So, of course, if people, instead of traveling by cars, use the train more, or they use more car sharing, electric bike, which consume less energy than cars, of course, we can assume that there is a peak in transport energy demand, but for sure not in 2026. And you see that indeed a transition implies several assumptions. And why the fact that these energy demands peak has an influence on our capability to revert to renewable energy? Because renewable energy overall is less reliable. It's not really something that we can regulate. And therefore, if we want to rely on this energy, it's necessary that we reduce our energy demand. And it's necessary that we make sure that essential sources of energy, like transportation, like industrial production, in a way rely on more efficient solutions for their production chains. Okay, so this is why they have to assume a peak for transport energy, at a peak for manufacturing energy demand in 2039. A peak in manufacturing energy demand means that industries should reach a cap for their energy requirement. This is something really demanding, really not so likely, okay? So if you navigate this picture and then you see the predictions for the green part. So 2024, which has been already passed, light EV reach cost parity with internal combustion engine vehicles. So this means electric vehicles reach cost parity with traditional vehicles. We know that this didn't come true. They are still more expensive. Because otherwise, it's not accessible to people. And what counts is the global mass of people. And the global mass of people doesn't have opportunities for investing money. And therefore, we really need, if we want to promote the use of electric cars, besides wondering how the energy is produced, we have also to make sure that these are convenient, otherwise it's not possible. And 2026, gas overtakes oil. This will not happen, okay? And still gas is anyway fossil fuel. And 2033, half of all light vehicle sales electric. This is too optimistic. Here there is another prediction, 2033, nuclear peaks. I can't really see how nuclear can peak because unfortunately, in order to peak the nuclear, we need to reduce our energy demand a lot. So if you navigate this graph, you will see what are the essential requirements for an energy transition and for the energy transition that we would like occurring, okay? And here the main problem is that potentially there is enough solar energy for covering our needs, potentially. And if we put together solar energy with wind energy, with everything, there is enough of it. The problem is to be able to get it when it is needed and the spatial distribution. Fortunately, energy can be transferred between countries, but in order to transfer it, we need international cooperation. So you see that in this, the problem is very complicated. Let's try to understand some more, okay? Before understanding some more, here there is another interesting figure here. I think we can keep it on the screen in this way. So this is a scenario which is called the 2050 energy mix for Europe, not all of Europe, main countries. A scenario showing the share of renewables by type after transition to 100% renewables and improved energy efficiency. Improved energy efficiency for the reasons that we mentioned earlier. Okay, and here you can see the potential share. Let's look at Italy, for instance. Italy, great majority from solar plants because there is indeed in Italy a lot of sun, okay, especially in the south. And the other contributions are from offshore wind production. It's an interesting opportunity. This graph is also useful to start learning what are the different types of renewables which we may consider. And then there is onshore wind in Italy. I would say Italy is, the dark blue is onshore wind, which means on the land or in any way close to the coast. Offshore means in the sea, but in the sea far from the coast. And this is a small contribution for Italy, but in other countries you see that it's an important contribution. And then there is the green that is others, including wave energy, geothermal energy, hydro, and tidal turbine energy. And keep in mind these types, renewable types, wave energy. Waves, they store a lot of energy and with very small friction. So they last for a long time. Geothermal energy, very important. Hydropower. For Italy is a significant source, hydropower. By the way, at global level, hydropower represents 17% of electricity production. Electricity, not energy. Energy is about 2%. But electricity production at global level, hydropower is about 17%. Hydropower is very important. Unfortunately, requires artificial reservoirs, which not all the people like. And then there is the light orange, solar thermal. What is the difference between, there are two main types of solar energy production. Solar thermal means that the plant produces heat, and solar electricity, the plant produces, like photovoltaic panels, the plant produces electricity. And there is a difference. Of course, if we want to use the solar energy for heating a house, it's more convenient to use to go a direct conversion between solar energy and thermal energy. If instead we want to use the solar energy for running a car, it's more convenient and it's necessary to go through the transformation in electricity. But when we can avoid further transformations, is much better, as we will see. Other countries, like if you look at Germany, it's a different story. There is a lot of onshore wind. There is a lot of solar plants. But it's interesting to try to see what is our expectation. Of course, after transition to 100% renewables. Keep in mind that putting together several different sources is extremely important. So if I was in a country with the whole disk covered by one source only, I wouldn't be very happy. It's very important diversity of sources when we need to exploit essential resources like energy, water. It's important to rely on a diversity of sources because the system becomes much more resilient. Diversity in a system, whatever system it is, means resilience. Remember that, okay? And it's particularly important for social systems to reaffirm the concept. A social system is resilient if it is diverse. If a system is not diverse in terms of social system, in terms of ethnicity, in terms of healthcare, in terms of politics, is going to become less resilient. There are several scientific studies on that. Okay. Okay, after this premise, let's try to focus on some more detailed technical details. Okay, first of all, there are, let me open this table in, it's not a figure. Okay, let me expand it then. There are 6 forms of energy which are listed in this table. They are listed in the column and in the vertical direction and horizontal direction, in the columns and the rows. So 6 forms of energy, you have to, anyone who is interested has to get very clear what the 6 forms are. So thermal energy, chemical energy, electrical energy, electromagnetic, kinetic, nuclear. Some of them are very clear to us, like kinetic energy is the energy of a moving body, or thermal energy related to the temperature, related to heat. nuclear energy, it's clear to all of us. I mean, it's the energy that we can derive by breaking an atom of a given element, okay? Electromagnetic is the energy that is originated by a magnetic field. Electrical energy is very clear. Chemical energy is the energy that we can get from chemical reactions. And so what is important to have clear in our mind? That it is possible for us humans to perform all the transformation, any possible transformation between one form of energy and the other 5. So we can, for instance, transform thermal energy into chemical energy through, look at the table, endothermic reactions. So these reactions where we needed to supply heat in order to form a new chemical matter that once it's broken can give back the energy. Okay. Other very simple examples: chemical energy can be transformed to thermal energy through by lighting a fire. So the combustion is a transformation from chemical energy and by producing thermal energy. And humans are used to do that since a long time ago. Another example, chemical energy can be transformed to electrical energy through batteries. In the batteries, we know there is a chemical reaction that is producing electrical energy. Okay. And then there is any possible transformation. Another very interesting example. Chemical energy is transformed in kinetic energy through the muscles. So this transformation is what we are used to do during our history. Okay, transformation of chemical energy in the form of sugar, fat. We burn sugar, we burn fats, and produce in order to produce kinetic energy. This is why we know that if we want to lose weight, we have to run, for instance, or to make a sport activity in general. And electromagnetic energy can be transformed in thermal energy through solar thermal panels. And or electromagnetic energy, sun radiation is electromagnetic energy, can be transformed into electrical energy through solar photovoltaic panels. There is somewhere the photosynthesis. Where is it? Probably, oh yeah, it's here. Electromagnetic energy, again, the sun, to chemical energy, photosynthesis. This is what the vegetation does, okay? Why chemical? Because vegetation grows up and forms chemical matters, like wood, that once broken, once we provide heat, they once we light a fire, they can produce heat. Okay. There are some examples that are not very familiar to us, like electromagnetic energy. We can transform it directly into kinetic energy. So the solar energy can be transformed directly into kinetic energy through solar sails. What are the solar sails? These are used in spacecrafts in order to propel, to move these spacecraft into the space by using solar radiation. We still cannot use extensively the same technique for moving cars, for instance. The reason is that in the space, there is no atmosphere. You have a direct exposure to solar radiation. So solar radiation is not in a way filtered by the atmosphere, and there is less friction because there is no atmosphere. But this is indeed an interesting opportunity. nuclear energy can be transformed into thermal energy through the nuclear fission or fusion. And this is what is used in the nuclear power plants to produce electricity. Because once the thermal energy is produced, then we can use this thermal energy to produce electricity through the generation of steam. Perfectly. Now, what does it happen when we transform energy? Transforming energy is very useful because in this way, we can move it. Think about hydropower. We cannot move water, it's too heavy. And therefore, what we do is to generate electricity and then we move electricity. But we know one thing. We know that any transformation implies a waste of energy. So for generating hydropower, we say that when a power plant has an efficiency of 0.75, it's very good. What does it mean, an efficiency of 0.75? It means that only 25% of the energy is lost. But then, in an hydropower plant, you transform the energy, potential energy of water that is stored at high elevations. You transform it into electricity and you have 1/4 of it that is lost. And then you have to move it. And when you move electricity along the wires, additional energy is lost and there are other losses. And this is a matter of concern. Energy efficiency also means that we have to try to reduce the losses. And this is the key, because think of the energy that is in nature. When you look around yourself, think at how much energy is there. When you look at a river and you see a lot, the river that goes down, a lot of bubbles, a lot of turbulence, a lot of movement. This is really an incredible amount of energy. Or when you look, when you go out and you feel like you get really heated by the sun, can you think of how much energy we get from the sun? Or when you get into the wind, you really realize that it's something very energetic. So if we were able to use all of it, this is much, much, much more of what we need. The problem is that using all of it is impacting on the environment. The problem is that it's to some extent impossible. And the problem is that, we need to move it because we need energy at a specific place and specific time. It's not just enough energy. It's like water. It's not just enough water. We have enough fresh water for 10 times the human population of today. We have enough water for more humans that the Earth system can sustain. Problem is that we need water in a specific place at a specific time. It's the spatial and temporal distribution. So you understand why energy efficiency is important. And so when we make this transformation, what happens in energy losses? This is very interesting because energy transformation is related by the energy conservation law, conservation of energy, okay? And conservation of energy is precisely conservation. So the total energy of an isolated system remains constant. And therefore, energy losses should be a matter of concern. The total energy of the universe is constant. The total energy of the solar system is constant. The total energy of the Earth system is closed, but for the energy from the sun, which means that the total energy of the Earth system is increasing because we are getting energy from the sun. But if we look at the whole solar system, we can say it's constant. So what does it go? The energy that we consider that it's lost. So when we transform this energy in another form, is it true or not that it remains constant? Yes, it remains constant, but at this stage, we have to consider the second law of thermodynamics. the second law of thermodynamics says that heat cannot spontaneously move from a colder body to a warmer body. So heat can move from a warmer body to a colder body, but cannot move spontaneously from a colder body to a warmer body. And therefore, this means that this implies that when you make an energy transformation, you produce heat. If you produce heat, like for instance, in hydropower, where does it go, the 25% that is lost? Unfortunately, it goes in heating the pipes, heating the turbine, heating the environment. And once we have warmed up something, we cannot we cannot get back that heat spontaneously. Or we can only use that heat to transfer energy to a colder body, not a warmer one. So what does it mean that the energy, that we cannot use this heat? It means that the energy that went to heat cannot be used to produce more work unless we transfer the heat to a colder body. But you understand that once you start warming up, colder bodies may become more and more difficult to find. So when we reason with the universe, the second law of thermodynamics implies that the energy is constant, but it is increasing the temperature of the system, of the whole system, which means that we will get to a state where the universe will have the same temperature everywhere, and this energy cannot be used anymore to produce work. This is called the theory of the final death of the universe, because when the universe will get to this stage, which is also called max entropy, when the universe will reach the maximum entropy, the energy of the universe will be there, but we will not be able to use it anymore to produce work. This is very simple. It's like predicting that everything has an end. Like, for instance, the Earth system, for sure, has an end. Will have the same fate as Mars, for instance. We will lose the atmosphere, we will lose the magnetic field, we will lose probably water. This is something that is clear, obvious. And overall, it is governed by subsequent energy transformations, which will, in a way, produce a progressive decline of our capability to produce work with available energy. There is one thing that we should note, however, that biological systems, they have the capability of absorbing heat and produce, and in a way revert this system. So biological systems are in a way slowing down this process through a biological process. But still, it doesn't change the final conclusion. Okay. So what I mean, the second law of thermodynamics is a physical law, which excludes the activity of the ecosystems, which through, in a way, can slow down. This process can be an exception. So you understand that it's very important that we try, when we make these conversions, be very efficient to minimize the amount of heat that is produced. So there are some of these transformations that are very efficient. Other transformations instead imply a huge decrease, a huge production of heat, and a huge decrease of the capability of our energy system, our energy, available energy to produce work. Okay. Anyway, key message, remember these 6 forms of energy. You may find in the final quiz of this exam a question like, how many forms of energy do you know? How many types of energy? And or there might be some quiz question listing, making questions on these on this classification. Perfect. A second interesting classification of energy. Let me go back to the PowerPoint, which I think it's oops, sorry. Here we are. Okay, here we are. Okay. Second law, thermodynamics, okay. Energy degradation, okay. Second classification. Energy can be divided in 2 categories. This is a very important technical classification: primary energy and secondary energy. Primary energy is consists of unconverted or original fuels. Secondary energy includes the resources that have been converted or stored. So, primary energy sources, examples: petroleum, natural gas, coal, biomass, flowing water, wind, and solar radiation. Solar radiation is the first source of energy. Secondary energy sources. I will go back to this slide, okay? Just 1 second, and I want first to define what is the secondary energy. Secondary energy cannot be harnessed directly from nature. So you cannot directly harness, for instance, electricity directly from nature, or let's say, in principle, it is possible through the thunders, okay? But actually, also the thunders are originated by a transformation. It is, but anyway, I understand that this can be debated. In any case, I to focus on the fact that this classification have always a green zone where it can be debated whether. But in any case, we can say that in practice, we cannot harness electricity from thunders, unfortunately, and therefore we can safely say that electricity is something that is derived from, for instance, from flowing water through hydropower. So it cannot be directly harnessed from nature. Another example of something that could be debated: oil is considered to be a primary energy source because it is directly available in nature. Of course, one may say, originally it was not directly available. It has been formed through a transformation, but the transformation was not driven by humans. It is something that is natural, and for this reason, it is classified, oil, as a primary energy source. Okay, I will give you other examples. Primary energy can be non-renewable or renewable, and renewable energy we already define how we define it. Okay, so let me just give. I think there must be a table Okay, here it is. A table summarizing what are the main sources for primary energy and what are the main forms of secondary energy. Please try to fix in your mind this figure, because the examples are very significant, maybe also the subject of questions at the quiz. So primary energy, crude oil, okay, crude because without transformation. If you think of the fuel that we put in the car, is not crude oil, okay, it has been transformed. So it may be already considered a secondary energy. Anyway, oil, crude oil, primary energy. Hard coal, again, hard means no transformation of coal, is a primary energy. Natural gas, perfect. Natural liquid gas, fine. Nuclear energy is considered to be a primary energy source because it is available in nature. Okay. Waste is primary energy. It's available in nature. Of course, you know that we can burn wastes to produce electricity or other forms of energy, and it is available in nature. It is not something that we transform. Wind energy, primary energy. Geothermal energy, primary energy. Biomass, hydroelectricity. Hydroelectricity, I mean, it's we mean with the hydroelectricity the flowing water. Okay, so don't be confused by the use. I wouldn't use, this table was not done by me. I wouldn't have written hydroelectricity because electricity is a bit confusing. Anyway, when we talk about, when we say hydropower is a primary energy source. It's available in nature because it's power, and power is fine. I wouldn't say hydroelectricity. Wave and tidal energy, of course, these are available in nature. They are primary energy. Secondary energy examples, petroleum products like the fuel that you put into the car. Okay. Manufactured solid fuels. There are many solid fuels that are manufactured, derived by coal, derived by other sources. Manufactured gases, etc. Electricity and heat. Okay, biofuels, these are also secondary energy. What is the difference between biomass and biofuels? Biofuels are derived by biomass, can be derived by biomass through transformation. Okay, and in fact, you see these arrows here connect through transformation, for instance, the biomass to biofuels. And through transformation, hydroelectricity to electricity, and so forth. Okay, and then we can better understand the slide that was here. So petroleum, natural gas, coal, biomass, flowing water instead of hydroelectricity. Flowing water is better. Wind, solar radiation. These are examples of primary energy sources. There could be other examples besides what is written here and besides what you find here. There could be other examples. And the driving concept is whether the energy source is readily available in nature or whether we need a transformation. Good, let me go back to here, and this slide was already discussed. And okay. Yeah, an important consideration, I'm just looking at what I forgot to say. Although most renewable energy sources are sustainable, some are not. For example, biomass sources are considered unsustainable at current rates of exploitation. Because, biomass sources means very often landfills, so it means collecting wastes, organic wastes, putting these wastes in a suitable location and producing through the biomass degradation, producing electricity or producing heat. But on the other hand, this is something that is not really sustainable because it requires a lot of time for a landfill to degrade, and the site that has been used for a landfill cannot be recovered, cannot be removed after degradation and used again. Okay. Hydroelectricity here, there is written that is meant to indicate energy contained in flowing water, hydropower, and therefore it is primary. So here it is explained why hydroelectricity in the table is located on the left. Finally, primary energy is measured in tons of oil equivalent, TOE. Keep in mind, this is the unit that we use to measure primary energy, the oil equivalent. I think it is a very meaningful way of measuring energy in technical terms, and it is very meaningful in our context because it is really important that we measure any energy that we produce in terms of oil equivalent. Let's make the break. Questions? Good. I'm stopping camera and micro and see you in 15 minutes. I apologize for the longer break. As I said, I'm not feeling very good today, so I had to make a longer break. I apologize again. Okay, so let's move forward. First of all, energy production in terms of global emissions. I think I have a graph. I jump forward in the slides. Okay, here it is. This is a nice graph. Okay, it's not easy to be understood on the fly on the blackboard. So I just want to draw your attention on the percentage here. Basically, the inner circle is the subdivision of human emissions based on the related human activities. So energy production is 73%, and then there is agriculture, forestry, and land use, more 18%, and then waste, 3.2, industry, 5%. First, I think it should be noticed that the other circles basically explain the subdivision of each macro category and subcategories. So, for instance, energy in agriculture and fishing, 1.7%. You cannot read here. I'm reading for you. Fugitive emissions from energy production, 6%. And then transport is 16%. So energy to transport is responsible for 16% of the emissions. Energy used in buildings, which is also related to heating, is another 17%. And then energy used in industry is 24%. So if you want to estimate the total emissions from industry, these are 24% plus 5% of direct emissions from industry, you get to 30%. So when we say energy, actually energy means a lot of things, and this diagram helps to understand. But what is the main message here is that energy production, which is something that we need for industrial activities, for agriculture, etc., is taking more than 70% of the human emissions. By the way, aviation is taking under energy, because there is another circle giving more subcategories. Aviation is taking 2% of emissions. Just to point out that sometimes we talk about traveling, reducing our plane travel. Actually, the plane travel stands reducing flights is indeed sending a clear message to the community. So it is something that is important because it's clear. The message is like stop using the car. Stop using the car and using a bike. These are clear messages to the community. They are very important. But in terms of real contribution to efficiency, to emission reduction, it's not so important. So even if we, in a way, abolished aviation, we would save only 2% of the human emissions. So it's not very important. The same thing for private cars. Private cars are not really contributing that much, but the message still remains important. Okay? And this diagram is for our working data, so you can get the updated version because this is, I think, is 2 years old, but this is the main message, which is important in order to understand the connection between energy production and climate. So I go back with the slide. So energy, 73%, direct industrial processes 5%, waste 3.2%, agriculture, forestry 18%. And this is a recent assessment And again, if you're interested in the update, just download this graph, which I think it is very meaningful. Okay, so primary energy use. This is another figure, which I think is from 2015. In the web pages, there must be written the date. And it shows you the world marketed energy use by fuel type. And this is primary because if you see the categories, these are all can be considered primary categories. So nuclear is, okay, the vertical axis, the unit, is quadrillion of, I think it is tons of oil equivalent, but please check on the web pages because the acronym, I think it is equivalent to TOE, but I'm not really sure. Anyway, it gives an idea of the relative importance. So nuclear is the less important. The renewable are increasing, and with an increasing trend that is more evident after 2007, but still they are well below the natural gas, the coal, and the liquids, which means liquid means fossil fuels. So you see that indeed there is also the prediction up to 2035, which sees an increase again of the renewables, but still, you see the relative importance. We are still relying a lot on coal, natural gas, and fossil fuels. The first three up there are the fossil fuels. Here there is a world energy balance up to the year 2018. And so why I use this graph? I use this graph once again to show that the fossil fuels account for 81% in 2018. To highlight also that the wind energy, this is a global energy balance. The wind energy is the light blue up there, and you see that unfortunately is very small. The solar is very small. Geothermal is very small. What is still, what is noticeable is still much lower than fossil fuels, but what is noticeable is nuclear, and which is not renewable, by the way. But I mean, it's not renewable, but it could be considered close to renewable because the material that is consumed is very limited in quantity, and there is a lot of this material that is available in nature. Hydro is, as I mentioned before, about 2% of the energy production, but in terms of electricity is 17%. Biomass, it is indeed significant, and wood. Unfortunately, keep in mind that burning wood means producing emissions. It's not emission-free. In principle, no energy production system is emission-free because also hydropower produces some emissions, at least for building the artificial reservoirs. But still, these emissions are much lower than those that we get by burning wood. And also biomass is producing, I mean, in some cases, it could be also the biomass a carbon sink, but in some other cases is producing emissions, CO2 emissions. Anyway, this also shows that we are very far from the materialization of the transition that we are seeking. It's also interesting to see at the energy production at the geographical location, because, as I said, energy can be transported, but of course, we need some premises and an international collaboration in particular. Half of the global energy is produced by China, the United States, and the Arab states of the Persian Gulf. Okay? Half of global energy. The Gulf states and Russia export most of their production. largely to the European Union and China, where not enough energy is produced to satisfy demand, not enough energy is produced internally. While in Russia and that has a lot of natural gas, and the Gulf states, which own, they have a lot of oil resources, they produce more than what is internally needed, and they export. Energy production increases slowly, except for solar and wind energy, which grows more than 20% per year. But still, the percentage is very reduced. And therefore, even if you double it, you pass from 1% to 2%, which means that a long time is required to get a meaningful contribution. Renewable energy is emerging as an opportunity to decrease global emission, we know that, but in turn it entails a significant environmental impact. For instance, wind farms, there is a significant environmental impact in terms of visual of the landscape and in terms of noise. And the noise is really important. If you go in the proximity of wind turbines, you realize that the noise is important. And about solar farms, the environmental impact is again on the visual, and it's on the losses of soil for agriculture. Agricultural production is extremely important, is food production. So you understand that there is also a nexus between energy production and food production, which is extremely important. And this is why energy food nexus is another keyword that is very popular today. And there is another impact of solar farms, which is related to water infiltration in the soil. And there is less infiltration, which implies also some impact on groundwater recharge. Again, this is a significant problem. So it's interesting also to note that the global final energy use is given by the figures that follow. And it's the source is the International Energy Agency 2017. Residential, 21% of the energy. Transport, 30%. Industry, 30%, and others, 20%. This is energy use, final energy use, okay, which is different from emissions, of course. Okay. Global energy consumption from 2000 to 2021. So, in dependence of the different sources, here we consider 6 sources: coal, oil, natural gas, nuclear, hydro, others. And you see that there is, you see, first of all, the decrease in correspondence of the pandemic. The last but one bar of the histogram is the pandemics. So, but you see that there is a trend. There is indeed a decrease that we can observe for coal and oil, but the decrease is still limited to a small fraction of the increase that we experienced after 2000. But indeed, it is true that for coal, we are close to reaching a stabilization or the start of a decrease. This is in a way reassuring. For oil, it's too early to say that we are in a way moving to a decrease, especially because these figures are related to, they end up in 2021. So we are still missing 4 years here, 3 years here. I think these figures probably we can find an update. Natural gas is still increasing. Nuclear is more or less stable. This is quite known. The nuclear energy has increased a lot. The production of nuclear energy has increased a lot from 1970 to 2000, and then at the global level there was a stabilization. For reasons related to concerns mainly, hydropower is increasing, but not a very high rate, and the other renewables are indeed increasing significantly, but still their incidence is limited. Hydropower has another relevant feature that makes it very attractive. It's not only the fact that it's renewable, but it is also the fact that it is a form of energy that can be easily stored into the reservoirs. So we can use hydropower to fill the gaps, that are left there by the other sources. So coupling hydropower with solar energy and wind energy is an excellent solution. And in fact, we are starting to cover with solar plants, solar farms, the surface of artificial reservoirs. In this way, we can couple them more efficiently. So we can use solar energy when it's available, and when it's not available, we can cover with hydropower. And another interesting thing is that by covering with solar panels the artificial reservoirs, we limit evaporation, because it is true that water can be stored, and therefore water energy can be stored. On the other hand, it's also true that if there is evaporation, this is a reason for energy losses, which is a problem. So this is an excellent solution that is increasingly used, coupling solar panels on the surface of artificial reservoirs. The only problem is the visual, because it's indeed impacting. I mean, an artificial reservoir can be also considered like a natural feature, and is also supporting tourism, other commercial activities. If you cover the artificial reservoir with solar farms, indeed, the visual is not really good. As I said, water can be stored. And there is another interesting thing, that when there is excess of energy, for instance, because there is out of production from solar panels and from wind farms, we can use the excess energy to pump back water into the reservoirs. And therefore, it is like using a battery. The reservoir is used like a battery, like a storage of energy produced by solar panels. Of course, there is some energy losses, because pumping water back means using electricity to run a water turbine, a water pump, which means some energy losses. But still, it is an excellent solution, hydropower, to fill the gaps and recover the excesses of energy, because once again, electricity cannot be stored. You may think of batteries, but batteries have a very limited storage. We know, in fact, that electric cars have the main limitation of the limited mileage, because of the limited storage of the batteries. And also the batteries are a very impactful waste. The batteries cost a lot of money, and therefore, I mean, hydropower is instead an excellent solution, not for running an electric car, but for storing huge amounts of energy where an artificial reservoir is available, and for recovering energy excess. Overall, here the big question mark is the nuclear, because in order to fill the gap, I mean, towards the decarbonization, in order to find the energy to move towards decarbonization, the big question mark is the renewables, which are claiming to become sufficient to cover our needs. Is this reliable? And what is the B plan? If we cannot succeed to get so many renewables, because we cannot extend wind farms and solar farms more than a certain amount. What is the B plan? The B plan could be also the nuclear. And the nuclear has a future because with improving technologies, with nuclear fusion perhaps, which now it's not yet ready for producing energy at large scale, but in the future could be. And nuclear fusion would be really great. And if we gain the technology for producing in a serial way, in an effective solution, nuclear energy through nuclear fusion, this is really interesting, but we need some time. In fact, when we talk about decarbonization, the big question is when is the timeline? Because if we want a urgent decarbonization, nuclear or other solutions may be not yet ready to be undertaken, to be applied. But if we were willing to wait a bit more, wait a bit more means instead of 2050 as target date for decarbonization at the global level, if we could extend to 2080 in terms of improving technologies, this could be enough. So this is the big question. And of course, keep waiting is not reassuring, you know, that political orientations change and situations change in general. So when we realize that there is a urgent need, it's better to move forward quickly. On the other hand, we need to make sure that there are the conditions for moving forward. And so the question of the timeline and the question of the contribution of the nuclear energy is really relevant. Some other statistics, total world energy consumption by source. It's just interesting to see that, again, fossil fuels, 75, 80%, we are there. Nuclear, only 3%, which I mean, is not so bad. And renewables, 16. Now the percentage of renewable is around 20, 21. So indeed it's increasing, but renewables includes hydropower. And if you look at the renewables, you see a complete list. So biomass is still the big part of it. Biomass, we already discussed that it's not a very satisfactory solution. And after biomass, another important contribution is given by hydropower, which is here it's given to 3%. Of course, these statistics may change a little bit depending on the data that are used for computing them. And this, once again, sets the context, okay, these figures. Okay, when we talk about percentage of electricity that is covered by renewable, we are at about 30%, where hydropower is 17%. So renewables electricity, renewable electricity is about 1/3, a little bit less than 1/3 at the present stage. Renewable in terms of energy, about 20%. And when we refer to the 1/3 of renewables for producing electricity, about half of it is given by hydropower. This is another interesting graph that I found recently. Additions to renewable energy capacity. It allows us to understand what is the renewable energy source that has been increased more. The data on the sources start from 2017. Before than that, you can see in gray a progress of the total. First of all, you see after 2020, there has been a sharp increase on the use of renewable, and this is the result of the many programs that have been pushed forward, especially in Europe, towards decarbonization. What is what has been increased is not hydro. Hydro has not been pushed a lot for the costs, for the environmental concerns, and for the lack of sites, because you need sites for pushing forward the hydro. But on the other hand, there might be an opportunity for small hydropower plants. Small hydropower plants are defined in terms of max energy production capacity. It's less than, I think, less than 3 megawatt as max production. And they don't require any particular impacting facility. They don't require them. They use flowing water. So you put a turbine into a river and you just use the flowing water. And their capacity is generally enough to cover the demand of small towns or, I mean, very small groups of users. On the other hand, they can be distributed very densely because they are, if there is flowing water, I'm sorry, if there is flowing water, they can be put along the river frequently. And so they may be a kind of important resource for the future. So what is this important resource? Is distributed energy production, which may allow us to profit from those clearly distributed sources of energy, like flowing rivers in the mountains, which otherwise we couldn't be able to use. This is an interesting opportunity. What is the problem, the reservation? The fact that in order to set up a distributed energy production, you need also a distributed network of facilities, distributed network of small turbines, distributed network of energy networks. And there is anyway some kind of environmental impact because the water flow, the velocity of the water flow slows down. So the water flow, the natural water flow uses energy. The velocity slows down and therefore there are impacts on the ecosystems. So there are several requests, several applications for installing this kind of small plants that are rejected because of the concerns. But still they may be a fine opportunity. Actually, you see that now the hydropower is not increased a lot. What is increased is the solar in general, and the yellow band and the blue band. You see that indeed it's what has increased more, and wind production has increased quite a lot. Biomass is more or less constant for the reasons that I mentioned before. It's the sustainability. Okay. This is the total energy production by countries. You see the text on the right gives the meaning of the color. And first of all, it is the whole world. Okay. And here yellow is China, and you see the sharp increase after 2000. Light blue is Africa. There is an increase, but not so sharp. Blue is United States, quite stable. Green is Europe, stable, decreasing. Decreasing probably for the closure of nuclear energy or the closure of other energy plants that used coal. Some of them have been recovered recently. Dark green is Central and South America. This is, I mean, it is interesting just to notice that it is not uniform, the rate of energy production. The most important producers are up to today, China and I forgot. Red is red is the whole world. Okay, so the most important now is China and then United States. Renewable electricity. These are statistics that we already mentioned a little bit. Here, the text says the consideration that I already mentioned before, so the importance of the nuclear power. And then you see here what is the subdivision in the other renewable energy sources. Wind generation by region, Asia, Europe, North America, Middle East, increased a lot after 2010. And this is the distribution. Once again, it's of course not uniform distribution, that's fine. And once again, the problem is here the intermittency, the reliability. It's from our world in data, you can easily find the updated graph. Wind power density potential, this is just a map of average wind velocity, which explains where it's blue is lower velocity, where it's red is higher velocity. In general, it is the velocity is larger in very flat areas, and they are where wind speed can be more easily used. And I should have here also a global horizontal irradiation. This is a map of solar energy potential. This is what you would expect. We know what are the regions where there is more solar irradiation. Why it's important to look at these distributions? Because of course this highlights different opportunities, and therefore highlight what could be the gaps of relying on these energy sources. It's important where you see gaps in one energy source to make sure that there is still diversity in the energy production. This is this is the Global Solar Atlas. It's a public website that you can find where data are continuously collected on solar energy production, solar energy potential in order to support and promote the use of solar energy. Once again, unfortunately, there are problems of environmental impact, and these problems can be, in some cases, sustainable. In other cases, it's more problematic. Italy, for the geography of Italy and the morphology of Italy, and the fact that Italy relies on tourism, it's an important source of welfare. And the tourism is in a way affected by modifications of the natural setting. Still there are some reservations. So what is this? Climate Change Performance Index is a scoring system designed by the German Environmental and Development Organization, German Watch, to enhance transparency in international climate politics. So very low is dark red, low is red, medium is yellow, high is green. And I think it is taken also by a similar graph can be found in our world in data. It is interesting because it tells you something that it's not really matching our expectation. So very often our biased expectation brings us to associate higher performances in terms of environmental attention to the Western world. And it's not really like that, okay? As you see. It's interesting to see, for instance, that Mexico seems more affected than the United States in coping with environmental change by adhering to international climate politics. I think that this graph was elaborated during the first Trump term, and this is probably the reason why United States are poorly performing, and probably it's the same situation as today. Of course, enhanced transparency in international climate politics doesn't mean that the country is really effective against climate change, but still, it's an indicator. Here you can see a solar farm, and clearly you see the result and why the environmental impact is important. And this is the cost that is going down, declining price for photovoltaic panels, and it's about a decline rate of 20% average price decline for each doubling of capacity. And this graph goes from 1975 to 2021. Okay, I now have a few words to say in order in this lecture on the water food energy nexus, and a few slides to show on nuclear power generation. But I would prefer to stop here for today, and thank you for your patience, because I know that I lost a couple of 5 minutes, 10 minutes. But next week I'll be better. Questions? Okay, thank you.